My name is Georgi Radulov, and in this video I'll make the final step in the derivation of the PN junction current. So I'll start with the carrier concentration in the PN junction. This is here the space charge region, and this is the P side, and this is the N side.
So here the electrons, which are majority carriers here, which have the sufficient energy to diffuse on the other side, appear at this point with concentrations that we already derived in the previous video. Here the electrons are minority carriers in the P side, so they diffuse and recombine, and the concentration decreases decreases in space. Certain point they return to the thermal equilibrium value of the minority carriers electrons in the P side. The same with the holes. So from this point I will derive now the equation for the diffusion current in the PN junction. So in this video I illustrated how actually the current is conducted
in the PN junction. So the electrons leave here, so this is the externally applied voltage on the PN junction, and we have movement of electrons. Of course the electrons want to go from the negative side to the positive of the external voltage source. So they come here, and through the metal connectors they enter the N side of the PN junction. So here we see two phenomena that take place. The first one is illustrated with the electrons which are in the upper side. So let's assume that these have more energy, so their energy levels are a little bit higher, so that they have the sufficient energy to diffuse to the other side. As they enter here the P region, now they are minority carriers, and the chances that they meet holes and recombine are very high. So here you see that this annihilation of hole and electron pair is illustrated. So in this place, actually the electron is exchanged for a hole. So then the hole actually propagates in the opposite direction, and this is given by the polarity of the externally applied field. So the polarity is in this side, here is plus and here is minus. So this is the polarity of externally applied field, and this is electric field that exercises drift force on the carrier, so this is why they move. So the holes move along the electric field, while the electrons against the electric field. So at this place, the electrons are exchanged in the P material for the majority carrier, which is the hole. So then the hole move in order to be exchanged for an electron, and they originate from the metal plate. And the metal plate has abundance of electrons. So here very easily the hole is exchanged again for an electron, and then the electrons continue through the wire and just reach the positive side of the external energy source. There is another mechanism for propagation of current, which is from this side here, of holes, majority carriers in the P side, which propagate in this side, and they diffuse to the other side, from P to the N side, where they are exchanged for the incoming electrons, which are the majority carriers in the N side of the PN junction. So this is to say that some of the electrons that enter here will actually be exchanged for holes that diffuse from the p side. Therefore, to calculate the current, what we need is to know what are the diffusion currents of electrons from the n side to the p side, and what is the diffusion current for holes from the p side to the n side. So to calculate these diffusion currents, we look at the space distribution of the carrier concentration. So if you look at exactly the edge of the space charge region, this here is the concentration of minority carriers electrons. So at this point, the only current that we have is actually the diffusion current. Why? Because the electric field here, the direction is actually zero. If you look at the direction of the electric field, so here it is in this direction and here it is in this direction. But inside the space charge region, the depletion region, the electric field is in the opposite direction. So exactly here, of course, we don't have any drift currents. So in this contour here, we will have only diffusion current. And then as the concentration decreases, with a continuous function, this current, the diffusion current, is exchanged for drift current, which you can see here. So for example, here the illustration is that the drift current is up to this point, while for this line is up to this point. All this current here is diffusion current. So at the end, the current is the same current. So basically it comes out and comes in. Just that inside here, this region, the total current is partly diffusion current, partly drift current. Here, in the close to the terminals, is only drift, and close to the space charge is only diffusion. So here in between we have a transition, of course. So now the question is how to calculate the diffusion current, because if we calculate the diffusion current at the edge of the space charge region, we can calculate the whole current of the p-n junction. And we need actually the diffusion current at these 2 points for holes and for electrons. And then the total diode current will be the sum of the diffusion current of the electrons and the diffusion current of the holes. So these are the excess charge electrons that are injected from the n region to the p region. And these here are the excess charges of holes that are that are diffused from the p region to the n region. Here is the excess charge holes in the n region, so this part, and here is the extra charge, the excess charge electrons that are injected in the p region. So in the previous video we calculated these, and they are given by these expressions. And this is the excess charge as a function of the space x. So this equation actually gives this spatial profile of the concentration of the carriers. We are interested again in the edge of the space charge region. So there we can calculate what are the diffusion currents. So the diffusion currents are given by the diffusion coefficient, a electron, so sometimes it is noted with Q, sometimes as E, a question of notation, and the derivative of the excess charge. So this will give us the gradient of the concentration profile, which gives rise to the diffusion currents. If there is no gradient, there will be no diffusion, of course. And we have to evaluate this at point minus xp. So this is the edge of the space charge region. We do the same for the holes in the n site of the p-n junction. So we evaluate then the excess holes in the n region at the point of xn, which is the edge of the space charge region. If you do the mathematics, take the derivative of this with respect to x, you get this function, where L is, of course,
the diffusion length,
which is the average length in space for a minority carrier to propagate before recombining with a majority carrier. So the same equation, of course, for the holes. Again, we take the derivative with respect to space x of this function and times the electron charge and the diffusion constant. Then the total current, of course, through the structure will be the sum of the diffusion current of holes and the diffusion current of electrons. If we combine both in an equation, then we can put this as a constant in front of the brackets, and inside the brackets we will have the exponential dependence of the current on the externally applied voltage VA.
Now, you see that if we put negative VAs, this term will become 0. And then the total current will saturate to this coefficient -1 and this coefficient. And this will be negative current, and this is the current in the reverse biased mode for negative voltages. But what is remarkable here is that it saturates. It saturates actually to the value which is given by this coefficient, Js. And this is the reverse saturation current of the diode. So this, as you can see, is a technological constant which is given in many manuals. And then you can approximate the current to be the reverse saturation current times this expression, which is the exponential dependence on the externally applied voltage. And for larger VAs, you can simply simplify this current as the exponent of VA divided by VT, because this will be negligible. And then we will have here an exponential characteristic. So this is not really to scale, because this current in practice is extremely small. So what you see usually in the characteristic is something like this. Thank you very much for your attention. Bye bye.